Hello, everyone. My name is Mario Lanza. I am an associate professor of material science and engineering at the National University of Singapore. Today, I would like to talk about a very important and timely topic in which we have been working over the past 2 years. Its name is synaptic and neural behaviors in a standard silicon transistor. This is the outline that I will follow during my presentation. First, I'm going to talk about the deployment of artificial intelligence on edge. And then I will present the neural and synaptic behaviors that we have measured in our standard CMOS transistors. And finally, I will make the conclusions. So every day we are using more and more artificial intelligence, and all this intelligence is based on the deployment of artificial neural networks. In these networks, we need to perform a lot of mathematical operations to do the calculations. One of them, as you can see here, is the vector matrix multiplication, but there are many others. These mathematical operations are performed using graphics processing units, which are made of billions of silicon CMOS transistors that are being acting as switches. When we apply a voltage in the gate, we can form an inversion channel between the source and the drain, and this can allow us to emulate the zeros and ones of the binary code. The main problem of this technology is that we are in need of transferring data from the memory unit to the computational units all the time. And this is slow and consumes a lot of energy. Moreover, because it consumes a lot of energy, it is expensive, it wastes a lot of natural resources, and moreover, it cannot be integrated in mobile objects. So in order to overcome these problems, and also because this is a massive business, we are going to try to work on solutions for this problem. So in fact, if we analyze the needs for artificial intelligence, we can see that the previous example that I show you at the data center level is here, and each one of these GPUs consume a lot of power, in fact, even up to 1000 watt. However, there are many other electronic devices within the Internet of Everything that need to perform intelligence operations, such as, for example, recognitions of sounds, recognitions of bioelectronic impulses, recognitions of images, and this needs to be performed in the object, because otherwise we need to rely on a stable internet connection to the data center, which is difficult in mobile objects, and moreover, the data transfer to the data center, it's still consuming even more energy. So in fact, one of the solutions that is being explored by many groups is to try to associate this computational circuit or microchip with the sensors that interact with the real world, to try to perform the artificial intelligence computation on the device, that is on the edge. So one of the most attractive electronic circuits to implement artificial intelligence is spiking neural networks. It is inspired in the way in which biological brains compute information. So these are asynchronous systems in which the information is codified in spikes with different frequency. The learning consists on adjusting the weights in the neural network. So we have the input neurons, to which the data is being introduced, codified with these different frequencies. And then we have some internal layers or hidden layers, and then the output layer. So basically, depending on the combination of the inputs, which are related to the data that we need to recognize, one of these classes in the output layer, one of these outputs will be activated, will be the one that is spiking the most. So in this case, these neurons or these nodes need to exhibit a very non-linear activation function, and also it need to show one dynamic learning function that is called leaky integrate and fire behavior. So here you can see a little bit more about the mathematical model, but probably it's even more clear if we take a look to the schematic. You have in the input several neurons that are producing these spikes. These spikes arrive to the next neuron, and this one needs to integrate. So if these neurons are firing all the time, eventually the internal membrane potential will increase and it will surpass a threshold. When it surpasses a threshold, then at the output the neuron perform one impulse. And if these neurons stop firing, then the membrane potential will be reduced, and then we will need many more spikes to try to trigger this activation function again. So this is something well known, and there are different mathematical models that can implement this leaky integrate and fire and this neuron behavior. And here you have some of them, but not only the name, but also how these functions are implemented with standard CMOS technology. Here you can see for the example of an adaptive exponential integrate and fire neuron, which is being implemented in this article using several transistors and a few capacitors. The capacitors are particularly harmful because they consume a lot of area. Here you have another example that consumes even more area, another example here and here. And here I wanted to show you one example of an industrial microchip. This is a microchip from Intel called Loihi2 that it is a spiking neural network. We have checked at the patent of this device of this microchip. There is not as much information as we would like to get, but it was enough for us to understand the structure of the neuron and the structure of the synapse. This based on this block diagram and checking other academic publications, we can see that the size of each neuron in the chip is relatively large. So to try to reduce the energy and the footprint of each neuron in this spiking neural network, the community has been investigating different types of electronic devices over the past few years. One of them is called Memristor. So the Memristor typically is a device that has a metal insulator metal structure. And when we apply different electrical impulses, we can change the resistance of the insulating material that is here inside using different physical mechanisms such as phase change, metal ion migration, spin change in magnetic materials, or dipole formation and rupture in ferroelectric materials. So there are a few types of memristors in which the low resistive state is volatile. That is, when you apply the voltage, you can trigger the dielectric breakdown, but then this resistivity change is reversible. Whatever atomic modification of the structure of the insulator that we have made, it self-recovers when we switch off the voltage. So as you can see in this diagram, current versus voltage plot, what we call IV curve, you can see that it has a highly non-linear transition, which is what we want to make a neuron. And also, in this other article, it has been demonstrated that this kind of memristors can exhibit the leaky integrate and fire behavior. You can see it clear if you analyze panel D, because you can see that depending on the voltage that they apply to the memristor and depending on the frequency of the spikes, they can reach different firing times. Okay, this is the figure of merit that is demonstrated that this memristor device is producing this leaky integrate and fire behavior. However, memristors are still suffering from a limited yield and variability, which is the main problem when trying to scale up this technology. Here you can see one example. In my lab, we have made different types of threshold type memristors, this kind of memristors that self-recover to emulate neurons. Here you can see two different proposals. The first one is 25 micrometer square silver boron nitride gold devices. So we measure several devices. We achieve a yield that is relatively high using academic yield pass criteria, not a industrial yield pass criteria. So our yield pass criteria is if we have a decent on-off ratio of more than 5, and also if we observe more than 1000 cycles. And based on that, we observe yields that surpass 80%. And you can see here that we measure for device 1, 2 million cycles, device 2, 200,000, for this one, 9 million, 4 million. But as you can see, there is variability in the resistance of each device, not only cycle to cycle, but also from one device to another. For example, you can see here the resistance of this one is slightly larger than the resistance, for example, let's say of this one. Okay. So this is something important because all the memristors in the network need to be operating similarly. We have fabricated another sample on chip with this silver boron nitride memristors on the chip. In this case, the size is much smaller and they are integrated on the tungsten via that come from the third to the fourth metallization layer of the transistor. And you can see that we don't have ideal curve. We also see relatively high endurance, but we have significant variability of the levels from one device to another. So we have explored this behavior. We have tried to work with other technologies that could produce this kind of threshold type resistive switching phenomenon with leaky integrated amplifier and with highly non-linear transition, which is what neurons need to exhibit. And when we started this investigation, we thought on something that must be compatible with the CMOS industry, because when we try to work with novel materials or with ultra-scale emerging devices, normally the yield is very limited, the variability is very high, and this is something problematic. Even it is interesting for academic research, but for this topic, we wanted to try to do more, something more at an industrial level. So we explored the functioning of the transistor, as I have shown you before. A standard silicon transistor, when we apply gate voltage, it produces an inversion channel and it behaves like a switch that can emulate the zeros and ones of the binary code. There is no possibility under this operation mode to emulate this dynamic leaky integrate and firing response. It's very challenging. However, we noticed something interesting. In these transistors, as you can see here, this is the output and transfer characteristics of the transistors. This is something very standard that appear in most textbooks. However, we found something interesting. When we start to drive current along the channel, we normally produce a phenomenon called impact ionization. Okay, the charge carriers can collide with the atoms in the silicon network, and they produce electron hole pairs. I mean, free electron and hole pairs. The electrons flow towards the positive potential, and the holes normally are driven to the ground because the bulk terminal of the transistor is connected to the ground. As you can see, this current through the bulk can be large. This is a plot that normally does not appear in the textbooks, where you can see that at certain level of current, at certain level of polarization of the transistor, around 2 volts, we start to have a lot of current through the bulk terminal, okay? So then we thought what will happen if we try to remove this connection, and we will have these holes trapped here in the silicon, because there is no way they leak outside. Of course, if we don't apply any stress and we just wait, they will leak, but it will take some time. So when these holes start to accumulate here there is a P-N junction. So there is basically a diode. When the potential of this terminal increases above the threshold potential of the diode, what will happen is that this is a N-P-N junction. There will be this kind of bipolar transistor will switch on, and we will have an avalanche current that will flow from the source to the drain. This is what you can see here. When we increase the potential of the bulb, there will be this avalanche current, which is what we call punch-through regime, okay? So this is very interesting. It produces this kind of highly nonlinear transition, which is what we need. However, when we ramp the voltage down, this transistor still is on. Tends to recover, but it takes a lot of time to reach the initial state because these holes here, they have no way to leak, and it takes a lot of time. So basically, what we have done is to apply here one additional resistance, a variable resistance, which is basically a second transistor that we control the gate voltage, and adjusting this to a resistance value of around 10 to 100 mega ohms, we can reach the nonlinear transition with the reset self-recovery, let's say, phenomenon. And this is the kind of hysteretic behavior that I showed you before in the slide where I presented the Memristor-based neurons. And if we repeat this ramping of the voltage of the transistor for many cycles, you can see that we observe very good threshold type resistive switching phenomenon. This is very interesting. I have to say that when we did a multi-project wafer tape out, not all the transistors in all the chips show this behavior. Some of them show it, but some dies simply don't show this behavior. And we noticed that the reason is that there is a gradient on the doping of the silicon wafer. And what we need to do is to adjust the bulk resistance to the same value. We do this connecting the second transistor. And in this case, we can adjust that absolutely all the transistors in all the dies produce this behavior. At the same voltage, they fire transitioning from the same resistance current level to the same current level in the low resistance state. This is fantastic because, moreover, it is a yield of 100%. It always works. And actually, not only works for time zero, but also if we repeat the stress for many, many times, we always see the same. You can observe here, we have tested here these 7 devices with the same biasing protocol. And as you can see, we always observe very high endurance for this specific device. We simply stopped the test at 5 million cycles. This device didn't die, and none of them died. And you can see the cycle-to-cycle variability is low, but also the level of the states from one device to another is very, very similar. And as I mentioned, not only the variability is very small, but also the yield is 100%. All the devices show this. In this bottom part of the graph, I show you what happens when we use a different biasing protocol that is not optimized. We don't have as good characteristic as in the previous case, but still it is very, very reproducible. So if we optimize the biasing protocol, we can get a nearly ideal characteristic. This plot is basically what we always try to find and achieve for many, many years with memristors, and nobody achieved. Yet we achieve it with the cheapest element possible, which is the silicon CMOS transistor. So we have done many other measurements. Here you can see how this hysteresis can be controlled with 3 different parameters. The first one is the ramp rate that we apply. The second one is the gate voltage of the transistor. And the third one is the bulk resistance, which is equals to altering the gate voltage of the second transistor. But that was only for the nonlinear transition. For the neuron, we also need to observe the leaky integrated fire operation. And this is something we have observed by applying a sequence of pulses with different frequencies and different voltages. So as you can see here, when we apply pulses of nearly 4 volts with a frequency of 3.5 kilohertz, we need some specific time of around 14 milliseconds to let this device fire, to produce a spike at the output. However, if we increase the frequency, the firing time will be much shorter. Here you can see what happens when we change the voltage of the spike, the frequency of the spike, the duration of the spike, and also the bulk resistance. All this alters the firing time. And all this is for only one gate voltage. We still have the gate voltage of the transistor as an additional parameter to tune the characteristics. We have also calculated the firing time and the firing energy. We observed minimum consumption of 415 picojoules per micrometer, which is already very attractive. And interestingly, we have observed that the recovery time can also be controlled depending on the resistance that we put here. So this, you can see the different discharging, let's say, or leaking time for these holes that we accumulate. So based on this, we have managed also to implement synaptic plasticity with this pulse per facilitation and depression, and with this potentiation and learning behavior. This is also something that is being used for people who implement spiking neural networks. Finally, I would like to show you another additional interesting behavior. In the previous plot that I showed, the gate voltage that I was using was 0.3 volts. However, if I increase the gate voltage, I can achieve that the figure of merit of the transistor shows some hysteresis between the forward and the backward. It is not very large, but it is enough to produce stable multi-level resistance in the channel. And you will say, oh, this is a little bit weird because transistors are volatile elements, and therefore, how can it be possible that we are changing the resistance at the channel from the source to the drain? Okay, so by applying different types of stresses, we managed to find out that what is happening is that there is being a change on the threshold voltage of the transistor between the forward and the backward. And this is an indication that the reason for this resistance change is the charge trapping and detrapping at the gate dielectric. We have also applied this kind of stresses sequentially using pulses, and we can also observe this kind of synaptic behavior for thousands of cycles, which is also very interesting. So this two transistor cell is what we have called neurosynaptic random access memory cell. It's a two transistor cell that can be operated as neuron or as synapse. It has high versatility because we can control the firing time of the transistor very accurately with different parameters. And for me, the strongest point is that we achieve a very high yield of 100% and minimal variability using a fully a technology that is already implemented. So this is something very important because as we are not using elements that are aligned to the semiconductor manufacturing chain, is something that we don't need to wait long time to achieve high yield. So we are now working on the monolithic integration of these two transistors in new microchips at the 130 nanometer node. We are exploring this phenomenon in transistors of the 28 nanometer node with high K dielectric, and we are hiring several circuit designers to fabricate spiking neural networks using the two transistor cell that is integrated in the chip, as you can see here. This is the monolithically integrated cell. And actually, this last part that requires more circuit design is something that we have externalized. We are doing through my new startup company called Neomorphic. I hope that soon you will also hear a little bit more about this company. So finally, as a conclusion, we have biased the CMOS transistor in an unconventional way to generate punch-through mechanism due to the charge stored at the silicon bulk via impact ionization, and we use it to generate spiking neural networks with 100% yield. So basically, we have reinvented the transistor. This is the traditional mechanism discovered by Mohamed Atala and Dawon Khan in 1959, and now we are exploiting the punch-through mechanism to produce these spiking behaviors. And the second conclusion is that the neurosynaptic random access memory is a two-transistor cell capable of emulating the behaviors of electronic neurons and synapses with high versatility. Finally, I would like to thank all the members of my team for their hard work. Here I leave some additional publications from my group in different topics in case you want to check. And if any of you or your students are interested in joining my group at the National University of Singapore, either as a master's student, PhD student, postdoc, or simply for an internship, you can apply to one of the offers that I have published in the platform Web of Talents. And that's everything from my side. I hope you got excited with this topic as much as we are. Thank you very much.